Kimia is now a Ph.D. candidate at the University of California, Irvine. She received BS and MS degrees in electrical engineering from the University of Tehran, Iran, in 2010 and 2013, respectively. Her current research interests include navigation, analysis and modeling of signals of opportunity, and software-defined radio. Dr. Zak Kassas is an assistant professor in the Department of Mechanical and Aerospace Engineering and the Department of Electrical Engineering and Computer Science at the University of California, Irvine. He received a BS in Electrical Engineering from the Lebanese American University, an MS in Electrical and Computer Engineering from the Ohio State University, and an MSE in Aerospace Engineering, and a PhD in Electrical and Computer Engineering from the University of Texas at Austin. His current research interests include cyber physical systems, autonomous vehicle navigation, and intelligent transportation systems. We greatly appreciate the time and the work that Zak and Kimia have put into this webinar. Following the presentation, Zak and Kimia will take some questions. To ask a question, please click on the Q&A box on the upper left vertical navigation bar. So thank you for being here, and now I will turn it over to Kimia and Zak.
Thank you, Ken, for the introduction. Good morning, good afternoon, or good evening, depending on your time zone. Thank you all for attending this webinar. I wish I could see you all, but unfortunately I can't. It's a pleasure to be here and give you a little bit of an overview of our navigation paper that we were honored to receive the Burka Award for. So first, a little bit about who we are. So we are at the Aspen Lab, the Autonomous Systems Perception, Intelligence, and Navigation, which is located in University of California, Irvine, in Orange County, California. This is just a picture of the campus and the beautiful Southern California coast where we are located at. Before I start, I want to acknowledge the hard work of our students in the lab, my postdoc, Mahdi, PhD students, Joshua, Joe, Kimia, Ali, and we have a bunch of undergraduate students that helped us tremendously in seeing the great experimental work in particular that you will see later on. So it's no secret that future autonomous cyber physical systems will get integrated into our daily lives. Unmanned aerial vehicles will be tasked with surveying the environment, with mapping the environment, delivering urgent hurricane relief supplies, and intelligence surveillance and reconnaissance. They are envisioned to help in firefighting, package delivery, infrastructure inspection, even air taxi has been floated around. If you live in a congested area like Southern California, you know that this is a dream really to get to your job with no issues. And delivering urgent medical supplies, or even if you are too lazy or if it is too cold outside, it can deliver a taco to your doorstep. Also, ground vehicles are envisioned to enable search and rescue, autonomous search and rescue. You can see this in the concept vehicle that could go into difficult places for humans to maneuver in. They can go and rescue soldiers or rescue humans after a disaster. In intelligent farming, ground vehicles, autonomous ground vehicles are already being in use. In finding mines, and even cleaning debris from shores and from the oceans. And of course, everyone's dream, self-driving cars. However, before this dream becomes a reality, we have to address a critical challenge that GNSS has. We are all familiar that GNSS signals are extremely weak indoors to the point that they are practically unusable. They are very spotty in downtown environments. So a study, for example, a few years ago revealed that less than 50% of the dense Hong Kong downtown has reliable GNSS coverage. Now, what is more dangerous than the signal being so weak and usable in many environments is the signal is also so weak and susceptible to intentional or unintentional interference or jamming. We can go and buy online a personal privacy device, which is basically a GPS jammer. Now, it is illegal, of course, in the US. However, it is still available. And there have been numerous incidents where people installing those jammers on their vehicles or on themselves, interfering with safety critical applications, such as the famous story of the New Jersey truck driver that interfered with Newark Liberty International Airport navigation system every time he drove on I-95 past the airport. And of course, spoofers had jumped on the bandwagon and started developing spoofing code and even making it available for everyone to download to mess with GPS. And as we all know, GPS can be used and is used in safety critical applications. So it's not really a joke to mess with it, because it could result in consequences that are catastrophic. And there has been other incidents of jamming and spoofing that did cause lives. For example, North Korea jamming GPS over South Korea over a 16-day stretch a few years ago caused this 300-pound UAV to crash into its command and control center, killing and injuring 3 engineers. There have been reports of China trying to jam this US Air Force Global Hawk UAV, Iran claiming to capture the US drone via GPS spoofing. There have been spoofing incidents nearby the Kremlin in Moscow a couple of years ago, and the Black Sea. And just this year, there have been reports of spoofing in the port of Shanghai, nearby Ben Gurion's airport. And it's claimed that the British tanker has been seized in the Strait of Hormuz by GPS spoofing. So one way to circumvent this single point of failure in GPS or GNSS in general is to listen to signals of opportunity in the environment. Now, we live in a radio frequency rich world where we have many, many signals that are not intended for positioning, navigation, and timing. However, we can exploit them. And we have been very successful in listening to cellular signals, LTE in particular, and exploiting these signals for reliable positioning, navigation, and timing in the absence of GPS or GNSS in general. So I'm not going to go through the history of signals of opportunity. This has been a very hot research area in the navigation community. People studied signals coming from Wi-Fi, from cellular towers, from digital television, from low Earth orbit satellite, among others. We have had a lot of success in LTE, cellular LTE, and this just gives you an idea how prevalent LTE in our life. So as of 2018, we had about 4 billion LTE subscribers worldwide. In fact, people joke that people have access to LTE more than they have access to clean water or to even electricity in some places. And the number will rapidly increase. Now, you see a little bit of a dip around 2023, but that shouldn't be alarming. This is really as 5G is getting rolled out around the world. And in fact, LTE is the first system that will coexist with a future generation, which is 5G. So LTE will be here for years to come. So let me tell you some other useful things about LTE and why it is desirable to exploit these signals for navigation. So first of all, we receive those signals at a much higher power than GPS. And one of my students, Ali Abdullah, had demonstrated that in deep indoor environments, you can get more than 30 dBs higher carrier to noise ratio than what you can get with GPS outdoors. So he demonstrated about 75 dB hertz carrier to noise ratio in deep indoor environments. Now, this is a big deal because it makes it harder to jam these signals and also these signals become available in environments where GPS isn't very useful or usable. So that's one advantage. The other advantage is people are hungry for cellular connectivity. And probably you are one of those that as soon as your plane lands, the first thing you do before you tell your fellow passenger, welcome home, is you get connected back online and check your email or Instagram or whatever gets you excited the most. So these towers are abundant. They will dramatically increase in coverage. And we are talking here about several towers and companies providing this coverage simultaneously, which you can exploit at the same time. The towers are geometrically diverse by construction of the cellular infrastructure. So that would be desirable for geometric diversity if you're doing time of arrival type estimation. Also, LTE can transmit up to 20 megahertz signal, which is called the CRS, the cell-specific reference signal, and Kimia will talk more about this. So this gives us better resolution in time, which also will yield more accurate estimates, or more precise estimates to be specific. And of course, we like free things. These towers are transmitting signals for free, synchronization signals to be specific, that you can exploit without communicating back with the tower. So I have to stress here, whatever we are going to show you, this is very different than the cell phone that you carry in your pocket. We have designed a receiver that can simultaneously listen to any LTE signal in the environment, whether it's coming from AT&T, Sprint, Verizon, you name it, whichever provider. Those are providers in the US. So you can think of different providers in your own country. The receiver listens to the downlink signal. It starts producing navigation observables from those downlink signals. And you don't pay a dime, you don't communicate anything back, and you don't even have to be a subscriber to any particular network. Now, of course, there is no free lunch. There are challenges that you have to address for this to be possible. The first challenge is the E-Node Bs, which are the LTE towers. That's what they call them, E-Node Bs. They don't have necessarily known states. So these towers are not built for navigation purposes. So they don't transmit to you like GNSS satellites. They don't transmit to you their position and clock errors. So those are things you have to determine on your own. And this is what we will talk about later in this talk. Also, their clocks are not as stable as atomic clocks on board GPS satellites or GNSS satellites. Once again, timing is not as stringent with communication standards as it is with navigation standards. So they are typically equipped with oven-controlled crystal oscillators, which is more than enough for their purpose. And also, they are not perfectly synchronized. So they don't have the Air Force, for example, for them maintaining type synchronization like it does for the GPS constellation. So that's something that we will have to deal with in our frameworks, in our navigation frameworks. And also, you can't go today and purchase, on the market, a receiver that is capable of extracting navigation observables, giving you pseudo-range and carrier phase from these towers. So those receivers are still in the research phase and certain labs, one of which is my own lab. So hopefully in the future, those receivers will be on the market and they will be integrated in future chipsets. And last but not least, multipath. It's everyone's enemy, and it can be a friend if you are a PhD student, and that's what Kimia turned multipath into a friend and managed to get several breakthrough papers by studying how you can alleviate multipath, and she will talk about there. Now, I have to stress that multipath here is a bigger issue than GNSS because the towers have low elevation angles, so the signal really that you are receiving is coming with a bunch of non-line of sight components. So with here, I'm going to turn the stage to Kimia to start talking about the receiver design that she came up with, and some other interesting aspects to keep in mind if you want to exploit LTE for navigation.
Hello, everyone, and thank you for attending this webinar. As Professor Kassas mentioned, we can exploit LTE signals for navigation in GNSS challenged environments. But these signals are not designed for this purpose, so we need to have specialized receivers to extract navigation observables from these signals. Before I talk about the structure of the receiver that we proposed, we need to know the low-level model of these cellular LTE signals. So here you see this a frame structure of the LTE. So LTE uses orthogonal frequency division multiplexing, or OFDM, for its transmission, which means that instead of transmitting one sample of data over the whole bandwidth, we can divide that bandwidth into smaller bands called subcarriers, and then transmit each sample over different subcarriers. So, for example, if you see this is the bandwidth of the LTE signal, and each element here represents one subcarrier that we transmit in different samples of the data over that, and they're all transmitted at the same time. What you see here is the LTE frame, which has 10 millisecond worth of data. And each element here represents the location of the one of the data samples that we're transmitting on a specific subcarrier and a specific symbol time. What you see here is the only important signals that we care about for our navigation, called primary synchronization signal, or PSS, secondary synchronization signal, or SSS, and cell-specific reference signal, or CRS. The reason that these signals are important for us is that they're transmitted from all the eNodeBs. They're available for us even if we're not the subscriber of the network, and we can exploit them to extract navigation observables from these signals. PSS and SSS, they are transmitted to provide the frame timing to the user equipment, and CRS is transmitted to provide channel frequency response to the user equipment. So as you see, PSS and SSS, they have less than 1 megahertz transmission bandwidth. So this means that they have they're very susceptible to multipath. What you see here is a frame, an LTE frame with the lowest possible transmission bandwidth, which is around 1 megahertz. But LTE can have different bandwidths, and what we see in our experiments is that different operators, they use more than 10 megahertz, and the maximum can be 18. So you might have heard 20 megahertz, but that means that we have 1 megahertz guard band in different two sides of the data. So we have 18 megahertz band that is allocated to the CRS signal, but as you see, the PSS and SSS, they have only 1 megahertz. So this means that the CRS can provide a more accurate time of variable estimation for us. But as you see, CRS is scattered in the frequency, so we don't have any time equivalent of this signal, and we cannot use conventional receiver structures to extract navigation observables from the signal. So here you see the proposed structure of our receiver. Our receiver has 3 main stages. In the first and second stage, we acquire the signal, and then in the third stage, we have the tracking. In each stage, the nodes A, B, and C, they're connected to nodes 1, 2, or 3, and they perform some tasks. So in the first stage, we get these samples of the signal in the time domain, and then we correlate it with the possible sequences of the PSS and SSS. Since PSS is transmitted twice per frame, what we get as the correlation, it will have 2 peaks in the correlation. And the signal that has the highest peak represents the NID2, which is the sector ID of the cellular, the eNodeB of the LTE signal. But SSS is only transmitted once per frame, either behind the first PSS or the second PSS, and it shows the group ID of the eNodeB. So using these 2 NID1 and 2, we can also obtain the cell ID of the tower. So now that we have the frame timing, we can control our FFT and convert the signal into the frame domain, and we can now go to the second stage. In the second stage, we now can have the signal in the frequency domain, and using the received signal on the subcarriers that are allocated to the CRS, we can use a more sophisticated algorithm like a split algorithm to refine our time of variable estimation. And then that time of variable estimate can be divided into the sampling time. The integer part shows can be used to refine the FFT window controller, and the fractional part can be used to be removed by phase rotation in the frequency domain. And as you might have noticed, we also estimate the Doppler frequency at this stage. So before we talk about the approach to estimate these values, we need to know the model of our received signal. When we have perfect synchronization, the received signal in the frequency domain is the multiplication of the transmitted signal and the channel frequency response plus some additional noise. But we know that we usually don't have this perfect synchronization. We have timing error, which can be due to the imperfect estimation of our frame timing, and we can have Doppler frequency effect. We can have mismatch between the oscillators of the receiver and the transmitter, and those can cause an additional term in our received signal, which depends on these errors. So our goal here is to estimate these EF and E theta, which represent our frequency and timing error. Before estimating these values, we need to first estimate the channel frequency response, which can be obtained by looking at the received signals on the subcarriers that are allocated to the CRS and then removing the effect of that CRS sequence. We showed that if we put these channel frequency estimates in one vector, so these are the estimates over different subcarriers. This vector has this following form. It has a noise term and a signal term. So the covariance matrix, if we derive it, it can be shown that it has a noise term and a signal term, and our goal here is to obtain the signal part and the parameters of this signal part. So there are different approaches that can be used to estimate these values. For example, super resolution algorithms. Here in this paper, we use a spread algorithm. I'm not going to go through the details of the steps of the spread algorithm. They're provided in the paper, and the proofs are also given in different literature. But the outcome of this stage is an estimate of our time of arrival estimation error, which can be used to refine the time of arrival. So next, we want to estimate the Doppler frequency. We showed that the phase difference between the received signal and two consecutive slots depend on the error of the frequency. And we showed that this error has this following form with this relationship with the Doppler frequency. So we can use that to estimate the Doppler frequency. So going back to the receiver structure, till now we discussed the second stage, where we refined our time of arrival estimation and also obtain an initial estimate of the Doppler frequency. Now we can move to the tracking stage, where we keep track of any change on the time of arrival and also Doppler frequency. In the tracking, we use a phase lock loop and a delay lock loop, or PLL and DLL, to track the carrier and code phase measurements. As I mentioned, CRS is transmitted and it is scattered on frequency domain, so we cannot use the conventional structures of the receivers that we already have, for example, GPS receivers, and we need to have and design a carrier phase and code phase discriminator functions that are designed for CRS signals. So for this purpose, we showed that the PLL discriminator function can have this form. We can take the phase of the received signal over all the subcarriers that are assigned to the CRS, and we showed that this phase is a function of the Doppler frequency, and the discriminator function statistics were also obtained. For the DLL, we used an early power minus late power discriminator function, but the difference between this discriminator function and the GPS is that we cannot use the early and late version of the code as what we have in GPS. We cannot just shift the code. But what we do is we have a phase shift on the code in the frequency domain, which is equivalent to a delay in the time domain. So now we can have early and late version of the correlation signals, and then that can be used in the delay lock loop discriminator function. This discriminator function can be shown that it has a signal part and a noise part with the following, as you can see, with this variance. So now we know the structure of the receiver. We want to know how well we can perform in a multipath-free environment in the presence of only noise. So we derived the noise variance of the carrier phase, and we showed that the open loop variance has this form. It depends on the carrier to noise ratio and the number of subcarriers that are allocated to the CRS signal. And here you see the results. The carrier phase 1 sigma error for different carrier to noise ratio and also different bandwidths. And what we notice is that for our practical applications, we see more than 55 dB hertz carrier to noise ratio, and usually operators transmit more than 10 megahertz bandwidth. So you see that the carrier phase 1 sigma error can be around 10 to the minus 2 degree, which is very accurate. The same approach was done for the DLL. The statistics were obtained, and again, you see that for typical scenarios, for the or practical scenarios, what we see is that the code phase error is on the order of less than 10 to the minus 3 meters. But these results are only in the presence of noise. What happens when we have multipath, which is very common in LTE since the received signal is from low elevation angle. So we showed that when we have a multipath environment, the discriminator function has an additional term which depends on the channel frequency response parameters, the delay and also the attenuation of each path. So to have an idea of how this affects the signal, we simulated the channel with one multipath and one line of sight. And the multipath had 6 dB lower power compared to the line of sight signal. And we showed that the error that can be caused by this multipath environment for different multipath delays and also different bandwidths can have around maximum of 12 degree error. But the good news is that when we have high bandwidths, which is more practical assumption, this error drops very fast for higher multipath delays. So the same evaluation was performed for the code phase error. Again, the discriminator function was shown that it has some additional term representing the bias caused by the multipath. And for the same multipath simulation environment, we showed that this error, when we have the lowest possible transmission bandwidth of LTE, this can reach up to 15 meters. But as I mentioned, in practical scenarios, we have more than 10 megahertz bandwidth, and this can be up to 2 meters, and it drops very fast when we have larger multipath delays. It's usually less than 1 meter. So with that, I would like to turn it over to Professor Kassas, where he will discuss navigation framework.
All right, so what I'm going to show you now is how we can navigate with these signals and how we will alleviate some of the challenges. So Kimia discussed one very important challenge, perhaps the most important challenge, is how do we extract observables? Well, the second challenge is we don't know necessarily the states of those towers. So one way to overcome this is to do what we call radio SLAM, radio simultaneous localization and mapping. This work has been conducted by some of my other PhD students. I will not talk about it there, but the idea is to simultaneously localize where the towers are and map them and navigate with them. So if you're interested in that, you are welcome to look at some of the work by my student Joshua Morales and Joe Khalife, who basically studied this. But what we will do here, it's not too impractical to assume we know where the towers are. We can survey the environment. We can use certain websites or use proprietary databases to know where the towers are. But obviously, we cannot assume we know the clock error states of these towers, basically the bias and the drift. So this is what we will do here. We will use an extended Kalman filter to estimate the receiver's position and velocity. So you see it here. We will constrain ourselves to 2D, to a planar environment. I will discuss later how we started looking at 3D on a UAV and some of our recent work. But for now, let's assume that the receiver is mounted on a car or on a ground vehicle or on a handheld device. So we will only estimate the position, the 2D position and velocity. We will also estimate the difference between the receiver's clock bias and every E node B's clock bias, and the difference between the receiver's clock drift and every E node B's clock drift. Okay, so, and we will assume we have N E node B's. This is a model of the pseudo range that we are extracting from our receiver. And we will assume that the receiver moves with a velocity random walk dynamics, okay, as simple dynamics as we can think of. And obviously, you can couple this with an inertial measurement unit. We have been looking into that and some other work, but let's not complicate the story here. So this is the experimental setup. This is the car that we used for the experiment. This is some of our hardware. What you will see here is Matrix. This is our multi-channel adaptive transceiver information extractor that we had developed to acquire, track, and produce navigation observables from LTE towers. And we are going to also use GRID. This is the generalized radio interfusion device produced by our friends at the Radio Navigation Lab at the University of Texas at Austin. This is a GPS SDR, probably one of the most advanced, if not the most advanced in the world. We will use it for ground truth purposes. So in this particular scenario, we were listening to 4 E node Bs from one operator. We have other experiments where we used multiple operators, including Verizon, T-Mobile, and Sprint. But for now, we will only use 4 E node Bs, and some of them are transmitting at a bandwidth of 10 megahertz, and then one of them is transmitting at 20 megahertz. So those are the experimental results, just to show you a comparison between the actual range and the pseudo ranges produced by our receiver. So how do we know the actual range? Well, we know where the tower is. We know the ground truth of where the vehicle is or where the receiver is. And we are plotting that versus the pseudo range. So it shows you how well we can do with our pseudo ranges as the vehicle moves. So obviously it's moving closer and further to different towers. This plot shows you the standard deviation, the error standard deviation, and you can see, some towers we are as low as 2 meters, and with E node B1 we are as high as 4.5 meters. This here compares our proposed receiver with the Esperit algorithm, the standard Esperit algorithm, and the ECAT algorithm. This is basically Esperit and the Kalman filter. And you can see this is the pseudo range of our proposed receiver in red, compared to, in blue is the Esperit and the green is the ECAT. And you can see how robust our receiver is in tracking the pseudo range, whereas the Esperit and ECAT has a lot of errors in the pseudo range that they're producing, which is very, very far from the true pseudo range. Not only that, but also our proposed receiver has a much lower order of complexity. It's computational complexity. It's on the order of n log n compared to Esperit, which is on the order of n cubed. So let me play a video here for you to show you the receiver navigating in a downtown environment, and that's in Riverside, California, in Southern California. Those are the 4 E node Bs in the environment. This is the trajectory in blue that the vehicle traversed. And what the vehicle is doing here, it's using the receiver that we demonstrated earlier, fusing those measurements through an extended Kalman filter. And I'm comparing the ground truth, which is in green, which is obtained with GPS, more than 9 satellites at that time, versus the LTE only solution. This is really, you can think of it even as a cold start with LTE. And this is the blue here is what we are estimating for the vehicle. And we are not fusing it with any other sensor. You can see how severe the multipath is in this environment. It's not the friendliest for signals, and we are very, very close. In fact, the 2D RMSE was 3.17 meters. Standard deviation was 1 meter. So those are some of the recent results. I will let Kimia talk about the framework for these results. In fact, she presented this in ION GNSS 2019, where she's looking now at the carrier phase measurements to obtain a more precise estimate of where a UAV is, and she was able to achieve sub-meter level navigation precision. So she will just talk a little bit about the setup of the different equations, and then we will show you real quick the video.
All right, so these are the results of our latest conference paper, where we wanted to see how well we can perform with using the pseudo-range, carrier phase measurements, and Doppler frequency. So the goal here was to remove the effect of the unknown clock bias and drift of the receiver. So we used the single difference measurements. So we had the measurements from multiple towers, multiple inode Bs. We consider one as the reference inode B, and we subtract the measurements of that inode B from other inode Bs, and by that we could remove the effect of the clock bias of the receiver. And then we assume that the clock bias of the inode Bs, they have very low drift. So we can initialize them and remove them from the measurements, and then we can assume they're constant over time. And this is a very practical assumption. If you have done experiments with these towers, you might have experienced the same thing, that these towers, they have very stable clock biases. So using these measurements, we also, as you might know, the carrier phase measurements, they have the integer ambiguity, which is also unknown. So we also put that in our state space model, and also we estimate that. So we not only estimate the position, but also the integer ambiguities according to these equations. And our measurements, again, is the pseudo-range, carrier phase, Doppler frequency, and also an altimeter. So the reason that we use an altimeter is is that we want to estimate our location in 3D. And all the towers, they have relatively the same altitude, so we don't have very good information in the Z direction. So we use that sensor in order to provide more information in Z direction. So here you see the results of our experiment. So we were listening to 4 different carrier frequencies. This is the setup that we used. We had a USRP to listen to 4 carrier frequencies at the same time, and it was sampling the signal, and it was recording it on a laptop for a post-processing fashion. And then after that, the experiment was performed in Mission Viejo, California. You see the experimental environment here. We were listening to around 11 towers at the same time. You see the locations of these towers on the right side. And the ground truth was obtained with a GNSS septentrion receiver, which has GNSS plus RTK plus IMU. So it was very accurate ground truth. And the red is our LTE solution according to the framework that I discussed. So you see that the result that we could obtain follows the ground truth very closely. And here we also discussed some approaches to detect the cycle sleep in our measurements. So I didn't show you how we can perform that, but you will see that there are some places that we have some mismatch. For example, here you see there's a difference between our ground truth and our solution, and this is mainly due to the cycle sleep that we had in one of our measurements. Since we only detect it, but in this framework we don't remove it, we just let the solution to converge to the true value after a few minutes. So our results showed that we can obtain sub-meter level RMSE, for example. 2D RMSE was around 81 centimeter, 3D RMSE was around 86 centimeter, maximum error was around 2.5 meter, and that was over 3 minutes of experiment, 600 meters trajectory.
Okay, yeah, so this is what we have for now. Once again, we thank you for attending this webinar. If you are interested in the papers, they are available online. We have also a number of patents filed for this work, both for different receiver designs that we had used on the ground vehicle and on the UAV. And to summarize, we showed you how the receiver works. We studied the performance in multipath free environment, basically the ranging precision, and the performance in the presence of multipath. We compared our receiver with the Aspirate and the ECAT algorithm. We showed you some ground vehicle navigation results and some aerial vehicle navigation results. And with that, I would like to thank the Office of Naval Research for funding this work, and we would like to answer any questions you may have for us.
Okay, Zak and Kimia, thank you so much. We have two questions. The first question is, how many PCI do you typically detect along the test trajectory, and how long does each PCI last? Did you experience cell drop-offs and pickup of new cells? If so, how do you calibrate newly acquired cells on the run?
So for these experiments, our trajectories were very relatively short and in one environment. So what we experienced was that we had all the cell IDs like over the whole experiment. But we can change the framework in order to consider the case that we have some measurements for a few minutes, and then we might drop. We might lose that cell ID, and we might again reacquire it. So for these experiments, no, we had them all at over the whole experiment.
So one thing I would like to stress out here, so as Kimia said, we didn't experience signals from towers dropping, so they were constant. And in fact, if you look at this video, it shows you that we are listening to towers that are miles away, and they're not even supposed to be servicing users in our location, and from different providers. So you can receive signals that are from towers that are miles away. Now, how do you deal with towers coming in and out? This is not too difficult of a problem to be addressed, and it has been looked at in other contexts, like in robotics. In SLAM, for example, some features drop in and out from the robot's field of view.
Okay, thank you. The next question, is the UAV above the cell tower? Since the transmit antenna is typically down tilted, are you in the side lobe of the transmit antennas? Did you experience reduction in signal-to-noise ratio and coverage?
Well, we are in the side lobe. So we have different experiments. Some we are exactly above the tower. In fact, we flew a UAV almost above the tower on our campus that we know exactly where it is. We are, for the most part, in the side lobes. There has been a study a couple of years ago by Qualcomm that discovered that, counter to what people thought, which is, yes, the tower, the antennas are down tilted to service ground users, the signals received by a UAV from the side lobes are more powerful because they are not experiencing any multipath. So the short answer is the signals up on a UAV are much cleaner and multipath free for the most part compared to signals on a ground vehicle.
Okay, well, thank you very much. We appreciate your time, and we appreciate those of you who signed in to listen today. We want to remind you that the paper is available for download from our website at ion.org. If you go to publications and search, you'll be able to find the paper there. It's free for anyone. You just need to be able to sign in with a free web account. And again, we appreciate Zak and Kimia being here today. Thank you very much.